Hi, welcome to the Signal Path. In this episode, we're going to try another repair. This is a Sencore PA-81, which is basically a stereo power analyzer. It has some really interesting features. It has completely independent left and right channels and has multiple inputs, some of which can be connected directly to internal loads up to 250 watts. And because it is completely independent, all the grounds and everything else are isolated from each other. It also has 2 meters with various sensitivity levels, can measure dBm and RMS volts and so on. It has built-in filters and even a built-in speaker that allows you to adjust the volume and listen to what it is that it is measuring, even when you're applying a really high power into it. Now this is a faulty one, and even though it's broken, they still are pretty expensive. They're really sought after because they're probably very rare and they're not made anymore. Now at the same time, I want to combine this with some other instrument that I have so we can do some nice THD measurements at very high output power from amplifiers. But first, we need to see if we can fix it. Now, aside from being faulty, someone has also modified this instrument. If you look closely, these units have some oscilloscope ports as well, meaning that if you're applying a really strong signal here, you can look at it on the oscilloscope with some attenuation. Not only that, these ports are supposed to be completely isolated, separating the ground of the oscilloscope, for example, from the negative terminals, which is quite handy, but someone has actually tied this in with some of the other inputs, removing that isolation. I guess it can boost the signal, but I definitely don't want to operate it like that. Okay, so I went ahead and zeroed these when the instrument is off as well as possible. This thing needs an external power supply to run some 12 volt input. Let's go ahead and turn it on and see what happens. There we go. Okay, not bad. The fan came on briefly. So these units do have auto ranging. You can see that the range selection is on auto. You can also manually adjust them. It's sitting somewhere in the middle of the range. It does react to my hand, so it's definitely picking up something. Very high sensitivity. Oh, that one just went crazy for a second. But I guess the only way to know if it's working or not is to connect some known signal to one of these channel inputs and see what happens. So let's do some input testing. At the top, I have a Keysight 33500B series waveform generator. This is a 2-channel instrument, so I can check the left and the right channel at the same time. I have set it to 1 kilohertz, 1 volt RMS on both channels, but the outputs are not enabled, so there should be nothing coming into the PA-81, but maybe some noise just coming from the Keysight here at the top. So both of these are set to measure from the blue inputs, the external left and right inputs, measuring RMS, and they're auto-ranging on the setting. So you can see they're sitting in 2 different places in auto-ranging, so that's not really a good sign, and they're reading some random values. So I'm already a bit worried about the fact that they're not settling in the same place. But let's enable the input and see what happens. So here's channel 1 enabled. Okay, this did something. Channel 2 enabled, and that did something completely different. So this is measuring 1 volt RMS, but on a completely wrong range. So something's going on. This is definitely not working. And on this one is measuring completely gibberish on a times 10. So both inputs actually have a problem, which is a little unfortunate, but they have different problems. So now I changed both channels to produce 0.1 volt RMS. And look at this one. This keeps hunting for the auto range. So that's already doing something which is not good. And this one is sitting actually on the right value. No, not the right value, close to the right value. It's off by a factor of 10. So the fact that this is often off by a factor of 10 is interesting because these ranges are all times 10. So something going on with the front end attenuation, potentially a range selection, and this is hunting and not able to settle down. So let's put them on some manual here. Okay, so that's wrong, unfortunately. Let's see, is it measuring anything that's meaningful? No, those are all wrong. And what about here? Times 1, no, that's wrong. That is also wrong. Yeah, okay, so none of the ranges are working. Okay, so I'm beginning to understand a little bit that there must be something with the front end, at least the range selection. Now, before we dig into it and figure out a bit more, we should understand how this instrument actually works by studying a service manual. So I was about to go to the service manual and I noticed something. So when I do the manual range selection, you can see I can jump between -40, -20, 0, 20, and 40. Now, I often hear a click in between some of these ranges. So from here, going to no click, there's a click there, there's a click there, and there's a click there. So there's something strange already. But look at this one. I go from the same thing, from here to here, no click, no click, 1 click, no click. So the relays are actually not switching. So that really confirms that there must be some front-end problem. And here's the block diagram of the Sencore PA-81. Now, despite the many things you see here, the fundamental operation of the instrument is actually not very complicated. It really only has two fundamental measurement capabilities. It can measure RMS voltage and it can measure DC voltage, and it can combine them and display them in various ways. One of the nice things are the isolated input and outputs, as I mentioned earlier. So all the inputs here are on the left side, and all the outputs, including the speakers, are on the right. And you can see that there are amplifiers and buffers in between and optocouplers in between, which means these really are genuinely fully isolated, sitting on different power supply grounds and everything. Now we can zoom in and take a closer look at this input side. There is a certain access of symmetry in this instrument because this is a stereo device allowing you to use left and right channels simultaneously, and the circuitry that follows each of those is identical because you can obviously do the same thing on both channels. But each channel has three different inputs. You can use an audio line, an external input, or a dummy load. In the case of a dummy load, you can dump all of that power into various series and parallel combination of power resistors, essentially emulating the behavior of some high power speakers. So therefore, at the same time as you're dumping the power on the speakers, you're doing all kind of other digitization and measurements on the signal. Therefore, you can measure power and calculate exactly what is happening to the audio signal coming in. For the other two inputs, you're basically allowing a smaller signal in, and you're playing with the gain in order to be able to measure that. So it's a nice, simple architecture. So you can see that these input relays, all they're doing is allowing you to select between which of these inputs you're applying, because you can only measure one at a time. And afterwards, we get what we're expecting, which is the attenuator control. So there's two different measurements that this thing can do. It can measure RMS to DC. So you can see that there is a circuitry here to convert RMS to DC. So this is the AC input measurement. And on the other side, we can see that there's a DC measurement circuitry, and there's a switch to switch between them. So the final stages, which are the A to D converters and the optocouplers to bring them back into the displays, they are shared between those two. So it can either measure the DC or it can measure the AC RMS. Now all of that is fine, and it makes sense. You can see your optocouplers in here for the isolated outputs, as I explained earlier. So this all looks good. But if you think about it, I was just using the external input on both of these. But when I was changing the ranges, not all the relays were clicking. So right away, this is the area we really should be looking at, because the attenuation control is what I think isn't working, or at least is one of the things isn't working, because the input certainly was getting past the input relay. Once you select it, it is fixed. So I suggest we turn our attention into this side. Now there's also attenuation control here as well. I don't know if these work or not, but I wasn't measuring DC anyway. I was really measuring only the AC signal right now. So I say we find where this is in the schematic and start paying attention to it. Now, before I forget, I want to revert the changes that were done to this instrument back to the factory original. If you remember, the scope inputs have been modified. You can see that these are coming from isolated inputs, but I think what they have done is that they've removed this and just tied it up to one of these inputs, completely removing this isolation between them. So first, let's go identify this and fix it back. And here's a look at the bottom of the instrument, where the main board of all the analog circuitry and the digital circuitry are actually located. And here, an axis of symmetry is also really obvious because we have our two channels at the top and the bottom. Now, even without looking at the schematic, some of the primary subsections can really be very obvious. So we have a whole bunch of relays in here and a whole bunch of relays in here, which are responsible for the input switching as well as some of the attenuation. And then we have some of the other amplification ranges and so on. Afterwards, we have our Intel processor and some EEPROM and all the various switches and the 74,000 logic and everything else in the middle. Now, if you look closely, you will be able to very quickly locate the modification that actually has been done. You can see these two cables have been tied together. This is directly connected to the input on the high power loads actually, and this one as well. So they have connected the oscilloscope to the high power loads, which is a little bit strange because if they're connected from the inside, they're also connected from the outside. You could just tap it from there. But this really should be coming from here. Luckily, the actual connector is still here. So they have preserved this, which is nice. They haven't thrown it away, which means we can just simply rewire it. And because it's completely symmetric, the other one is here at the very top. So before we do anything, I'm going to revert this back. Okay, so the inputs have been rerouted. You can see that the signal now goes from here and it's connected to this one and this one. Pretty quick change. Now that it's back to its factory original, I hope, then we can go ahead and look at the schematic. And here's the schematic of the instrument, and all of it is in one page, which is interesting, and it is laid out exactly the same as the block diagram with the position of the critical blocks. That's nice because you can easily follow it. So we have a whole bunch of front-end circuit stuff. Let's ignore that for a second and only focus on the attenuator because we definitely know there is a problem in here. And if you zoom in, you can clearly see the attenuation path. Now remember that we have an AC and a DC path, so the input coming over here is fully AC coupled because this section only deals with the AC signals. And that's nice because we can monitor this signal if we want to. Now, the way these attenuators are going to work is that we have two of them, so they can have four possible states. You can bypass the signal completely. You can see this path completely bypasses all the attenuation, basically providing 0 dB attenuation. Or you can switch this path in, it goes through this section, comes back again and does the same thing. So there's a few possibilities that you can organize this in, getting the various attenuation. Now, these relays are pretty simple. They're driven with an NPN with a series resistor on the base. There you go. They're not using MOSFETs in this case. And then there's a reverse diode for the coil there to protect these devices from the flyback charge that's going to happen there. So then you have the signal over here. That could be faulty. This NPN transistor might be dead, or the relay itself may be dead. Maybe the diode is shorted. There's a few different things. These are 12 volt. You can see driven from the 12 volt supply. So nothing really unusual. There should be exactly the same thing here at the bottom, and you can see that it is. So what they're doing is that they're getting the AC signal, passing it through this passive attenuation, and then they're passing it through this circuitry with this IC over here, which I think is a selectable switch. So you have multiple ways this signal can travel. You can go through here and then come back out and then get amplified and come back in. So they're doing some series combinations of op amps to getting the additional gain. So when you set this to 0 dB, you can get additional gain on top of that, or you can add attenuation when the signal is very large, and you get this really large dynamic range of gain with a combination of signals coming from the attenuators as well as the amplifiers. Now, we don't have to worry about the rest of this just yet, but we know that these are not switching, so we should really go back to these relays and find out what's going on with them. So let's start by checking the relays. Now, there are many ways to check to see if relays are working. Let's do something a little bit perhaps unconventional. Let's measure the inductance of the actuation coil of each relay to make sure that that is actually present, because we were not hearing any sound, which means that nothing was happening. So we can start from the relays. We can use the Rodenstrauss LCX200 for that, which I've done a complete teardown and review here on the channel, and we're going to measure the inductance of each of the coils, and we can also compare them that way. Okay, so let's start with one of the channels and one of the attenuation relays. Here's the first one. What do we have? Oh, 380 millihenry. That sounds about right, about a kilo ohm of resistance. Now remember that I have set the LCR meter to apply a very small voltage, 100 millivolt RMS, below the forward bias voltage of the protection diodes. Otherwise, you're going to be interfering with the diode forward biasing and conducting it. This way, the signal is just enough to measure the inductance. And we're also measuring it at 100 hertz, which should be good enough for these. So 380 millihenry, okay. So that relay seems to be okay. Let's measure the one next to it. Ah, look at that. Nothing. The other one doesn't register, which means it's not inductive at all. So the coil may be actually damaged. That is very interesting. So these are the two attenuated relays. Let's switch to the range relays, or the input selection, I should say. 280 millihenry, yeah, that sounds about correct in this part of the circuit, perhaps. What about the other one? 214 millihenry. Interesting. So the inductance of these two relays, and these two relays are a little bit different, even though they're exactly the same part number. Now the circuitry around it might be a little bit different as well, which will have some effect potentially. And let's measure the other channel. I'm measuring now just outside the camera. There you go, 370 millihenry. Okay, so one of the other ones is working. And then the other channel. Ah, look at that. Again, it doesn't work. Yeah, so these attenuation relays are indeed broken, and opposite ones are broken, which explains why the measurement results were not the same from each channel. And the other ones, 218 millihenry, yeah, it matches perfectly. To the other side, 214 millihenry. Okay, so let me mark these relays, the ones that are actually working and not working, and we'll take a close look at them. But you can see that the LCR method can actually tell if those inductors are the same or not. So now based on the LCR measurement result, you can see we have one faulty relay here and one faulty relay here, one on each of the attenuation section for each of the left and right channels. So, and they are not the same. Again, that explains why the channel measurements are not the same. Now, given that these have died and they're all the same part number, I would just replace all 8 of them because they're not expensive. And it looks like that these are maybe perhaps running too hot. I can see a little bit of discoloration on them, so maybe that's one of the reasons why they have died. The other thing I want to do is to measure the 12 volt power supply that's supposed to power these and make sure that it's not over 12 volts. Perhaps something might have gone wrong with the power supply section. We want to make sure that part is working. So the power supply section of this instrument is going to have to convert a single input into multiple galvanically isolated power domains, because all the left and the right channels, as well as all the input and outputs, are fully isolated from each other also. So they all need different power planes. So we have the AC line coming in, and it's going to get a little bit of rectification into a voltage regulator, which I think is going to generate 12 volts over here. And this is from the battery operation. I don't have a battery here, but it's a 12 volt lead acid battery can be connected. So the charging circuitry is also part of this. It does have some soft power on and some auto shut off functions, which are all handled over here. And this section then creates a plus 12 volt, which is coming from this regulator, and plus and minus 5 volt. But for all the left and right channels and all those op amps and opto-isolators and everything else, you need different power supplies. And they've done that by creating this little circuitry over here. Here they have an oscillator. This oscillator is going to switch these NPN and PNP transistors on and off into these transformers, essentially creating a DC-DC converter. And on the other side, we have full bridge rectifiers going into individual voltage regulators to clean them up, and then you get your plus and minus 5 volt on each supply. So from the original schematic, we saw that those relays are using 12 volts, so it's probably coming from here, but all these power supply sections should be there at the same time. So I suggest plugging this in and just making sure that they're really within tolerance. There's a few adjustments here and there. I think there is an adjustment here. You can adjust this voltage coming out, and there's an adjustment here which we don't need to touch. I think this is just the oscillation frequency and so on. Okay, pretty good. Well, before I do any measurement, I think I have figured out why those relays have died. So this instrument has an AC line, which we just saw. When you plug something in here, you can be a couple of volts over 12 volt, and that regulator at the input of the AC line will fix that for you. But there's another plug over here, which is where the battery goes. You plug in a 12 volt battery, and then you can plug that directly into this. This input, as we saw, completely bypasses that regulator. In fact, it says here that you need to apply 12 volts to it. But the power supply that came with the unit is 15 volts, and it doesn't fit in here. They've been running it by plugging it into this one. But when you plug it into this one, it means that your entire 12 volt power supply of this instrument has been running at 15 volts, overdriving a lot of things, including those relays, and slowly cooking them and killing them. I think that's why it has died. This should have been a 12 volt power supply, not a 15 volt one, and that's the cause of the entire problem. Now, having said that, we should still measure those power supply sections because everything in this instrument has been stressing for some time. And here's the other side of the instrument. Underneath this little plate over here, there's a fan and the high power resistors, which we don't need to take a look at right now. And here's the main power supply. It has the oscillators and the regulators and everything else. And I have my multimeter here, so we're going to measure those, but I'm going to run it from that 15 volt input just so we can confirm what I just said and then hopefully fix it after that. Let's start with the plus and minus 5 volt supplies, which are fully isolated for each channel. If I can catch those connectors here. Here's the 5.1, pretty good. And here's minus 5, that looks good. On the other side, here's 5 and minus 5. Okay, that's great. Now let's look at the suspect area. We should have also plus and minus 5 in here. If I can again catch those. Okay, here's 4.2. It's not quite 5. There you go. Here's a 15. That should not be 15. That's unfortunate, but it matches with schematic. Okay, here's another 5. Here's 14.67. And minus 5. Okay, so everything else is there. It just shouldn't be plus 15. So we're going to fix that. Little interesting attention to detail over here. So on this side we have the load, and on this side we have the power supply, and these are the inductors for the switching part of this. And you can see this plate over here even has a little cutout in there because to clear that little component there. I wonder if this is something they've added afterwards, and they noticed that there is some coupling from the oscillation, the noise of these inductors onto the other side, and this is an audio frequency, so maybe coming out of the instrument after that. So maybe they installed this just to isolate these two from each other. So I went ahead and modified the power adapter with a new plug-in here so it can be actually connected to the right port of the instrument. Here we go, plug it in there, turn the instrument on, and let's see if that power supply voltage is now actually in the correct range here. Go measure from here to here, and what do we have? That's not the one. There it is. There you go, 11.72. That's what it should be. So it was really being overdriven. So hopefully now we can go ahead and replace the relays. So I went ahead and removed all of the relays from the board because we know they've been exposed to this 15 volt supply for a long time. But I thought it would be interesting to take two of the working ones, run one at 12 volts and another at 15, and see what is the actual thermal difference between them when they're operating for some time and the power consumption of each one of them separately. Here's one of the broken ones, and it has a very large coil, as you can see, with many turns. The coil is just simply disconnected. So I have them both connected to a power supply. Let's see what happens when you enable the power supply. Okay, so both of the relays are on. You can see one of them is consuming 155 milliwatt, the other one 230 milliwatt. So that's a reasonable difference between the two of them, and that's going to change the temperature. Let's measure the temperature now. So here's the comparison between these two relays. So the one on the left here, that's from 12 volt, running around 38 Celsius. On the right, it can actually get as hot as 50. Now these are in isolation, sitting outside, so I'd imagine that when they're close together and in an enclosed space inside the instrument, these were probably getting much hotter than that, given specifically by the discoloration of the casing. So yeah, these relays did not have a good time. So I went ahead and I replaced almost all the relays. Unfortunately, the relays that I bought were from China and they were supposed to be new, but they were clearly unsoldered from some other board and some of them didn't work. So I have to use two of the old ones still. But I replaced them and I also looked at some of the transistors that drive these relays. A few of them had been degraded over time. I replaced them as well. Everything else looked okay. Check the cabling. Now it's time to turn it on, see if it's back to normal or not. And while we're here, I also recapped the primary power supply, especially with all the oscillators and everything that are in there. And this is going to be much nicer in terms of longevity of the device. Now, some of these capacitors were next to voltage regulators and they were getting quite warm as well. So this main one, I moved onto this metal body here. So basically it's going to be used as a heatsink. It all works out because the center tap of this particular regulator, 5-volt regulator, is ground, and so is the body of it. And of course, the chassis is ground. So it all works out and we're not violating any of the isolation ports. Looks good. So now let's do some tests on it and see if it still works after all the modifications we've made to it. So again, I have my 2-channel generator here, now connected to the audio line inputs. The audio line inputs allow you to measure much smaller signals because it has an additional gain stage there. So we can really test the entire dynamic range. And the 2 scope outputs are going now into the Tektronix 4 series. Now, interesting thing about this is that this is a B revision of the 4 series instrument. Now it has the new processor and runs essentially as fast as the 5 and the 6 series. Actually, looking at the performance of this, and given the fact that it has spectrum view and many other capabilities, this might actually be a better deal than the 6-channel equivalent of the 5 series. You have to do some comparison, but if you don't need all the bells and whistles of the 5 series, this is a really nice scope for what it offers you. So we can also, of course, monitor those out and we can see the THD on there as well. For now, let's look over here and see if those automatic ranges are working. So Dr. Pooch, are you ready for some tests? He ate a spider today, so he's super excited. So with the arbitrary waveform generator output disabled, you can see that everything is sitting at minus 60 dB scale very nicely. There's no oscillation, the meters are sitting at 0, and there's nothing on the oscilloscope. So I think it's in good shape when there's no input, which is pretty important. So let's go ahead and enable the input. I'm going to apply 1 millivolt RMS to both channels inverted from each other. And look at that, that's pretty good. This is 1 millivolt RMS here, 1 millivolt RMS here, and you have to multiply that by 0.01, which becomes exactly what it should be. So as I increase this, we should see the meter go up. There you go, that's 2 millivolt. Now it should switch to range. There you go, it did a range switch, that works perfectly. We keep going higher and higher. Here's 10 millivolt. So once we hit 20, we should also range switch. Oh, this one switched a little bit earlier than the other channel. There you go, the other one followed. So that's 22. Let's go all the way to 100. So here's 100. Yeah, it's measuring very nicely. Now we can go by 100 millivolt per division again. So here is now 1 volt RMS. Yeah, it's measuring very nicely. I think all those attenuators are working. So here's 2. Now it's full scale again. 3 will jump into new scale. 4, 5, 6, 7 volt RMS, and that's the maximum that ARP can generate. So yeah, it's measuring very nicely. The ranges are switching quite correctly. So let's look at the scope and make sure the scope is also producing the correct value coming out at the same time. So here's the display of the oscilloscope with 1 millivolt RMS at the input of this instrument, and I'm putting a 180-degree difference between the 2 channels so we can see them. So the signals are coming out nice and differential. Remember, the signal being measured here is fully isolated galvanically from the input, and in fact its amplitude is much larger. So when you are applying 1 millivolt RMS, this thing actually puts out 1 volt. So we have quite a large amplification, a factor of 1,000 between them. And I'm plotting the THD of both of the channels. Interestingly enough, there is actually a slight difference between them. There's about a 6 dB second order harmonic difference between the 2 channels. I'm not sure why that is because all the signals match perfectly. You can see the amplitudes are exactly the same. It must be the final op-amp that's just not as linear between the 2 channels. Perhaps it's slowly dying. It might be something worthwhile changing in the future. So I'm putting 1 millivolt, I'm getting 1 volt. And if I put, let's say, 100 millivolt, it's going to switch to a new scale. So here's 100 millivolt RMS. And everything's going to switch and the scale is going to change, and we get now back again a signal that is 1 volt RMS. But you can see how much cleaner it is now. That's because the amplification ratio is much smaller, so we're not amplifying the noise anymore. But the THD has not changed at all. There are some other spurious tones that are generated in there, some mixing. I'm not sure what this is exactly, but I think overall it doesn't look so bad. We can go down to 1 volt RMS. So with 1 volt RMS, basically the input and output are exactly the same amplitude. There you go, 1 volt. It's matching very well. Now I did adjust some potentiometers to get this. I'll talk about that on the schematic in a second, but I think overall the functionality is quite good. This galvanically isolated output has its own advantages because the signal is significantly larger. So if you're putting 1 millivolt, it's going to be very difficult to monitor with the scope, but here you have this very large signal to look at it. So even let's say an older scope should be able to display that. Now something like this will have no problem with that because it's very low noise to begin with. But overall I think it looks pretty good. We can also measure DC voltage using the external inputs here when you select the DC volt on the knob over here. So the right channel is tracking a little low. We're measuring 10 millivolt here, which is quite small of course. Now let's go ahead to, let's say 100. So here's 50. Yeah, now it tracks better. Interesting, it's a little bit low when the signal is small. And now at 100 millivolt, it's a little high. So there's some nonlinearity going on the right side, which may need some attention and calibration there. So let's go higher. Let's see, here is 500 millivolt, pretty good. Here is 1 volt, measures 1 volt without issues. Here's 2, it's going to change the scale. 3 volt, 4, 5, 6, 7, 9, and 10 volt. Yeah, nice. It does a good job doing that. It does have this ability to disable the loads if there is any offset. This is useful in some situations where you have a speaker that you're connecting to something and you don't want a DC connection on it, and there may be a bad amplifier that has a short and it's just connecting the power supply, and that will disconnect it so you don't put a huge amount of DC voltage across the actual resistors inside of the unit. So it's an interesting feature. So far we've been using the high impedance input of the instrument, the external channel input and the audio line input, but we do have the internal dummy loads which can be accessed via these terminals for dissipating a lot of power. So I want to make sure that those loads are actually present on both sides of this instrument. In fact, we can select what the value of that load should be. We have 2, 4, 8, 16 and 32 ohms which we can select, as well as open of course, and even has the over temperature indication if you're dissipating too much power over a long period of time. Right now I have 32 ohms selected, and you can see we're measuring about 32 ohms, so that looks pretty good. We go down to 16, we should be measuring that nicely. Here's 8 ohm, still looks good. Here's 4 ohm, pretty good, and here is 2 ohm. Now interestingly, because we're connecting to this port, it is monitoring the DC voltage to ensure that there is no DC voltage. When the resistance is so small, the DC voltage across it is very small, so it doesn't care about that. But look what happens if I go to 32. As soon as I go to open, you can see this light turns on because now the impedance is very large. There's a large voltage across here, many volts, and that is detecting that. So now if I go into this, it doesn't do anything. It doesn't select the load anymore unless I reset that. And when I reset that, we will get that load back. So that side of it is working really nicely. And similarly, the other side does exactly the same thing. All the loads work, and the DC connection detection also works over here. So very nice. I think we've tested almost all the functionalities of this unit. I think it's back to normal. Now, even though this instrument does not have a calibration instruction in the manual, it does have the full schematic. So we can use that and figure out what we need to roughly adjust to get some of the performances aligned up to where we want them to be. So for example, we can look in here. This is where the attenuation is in one of the channels. And right after that, we do have 3 sets of op-amps that can be put in series depending on their range switches. So you can amplify using them. And if you look carefully, there's a potentiometer here, one here, and one here. And you can use those to adjust the gain of each of these stages. In fact, this instrument has many potentiometers, too many in fact, and they are not very good quality, so you have to split the atom to get exactly what you're looking for. And various attenuation and adjustments and amplifications and DC offsets all can be found here. So for example, in the DC measurement section, which is over here, you can see we do have one potentiometer here, one potentiometer here, and they are all zero crossing adjustments as well as some gain adjustments. So you can play around with this to get the threshold between positive and negative all adjusted. That's all possible. It's a little tedious. I'm sure there is a clear instruction how to do it, but it doesn't seem like that's something that they even want the customers themselves to attempt. It is just way too complicated for that, and a little bit overly complicated in my view. But other than that, yeah, if you just follow this, you can make most of the adjustments. I forgot to show you that the speakers also work. They're completely independent on the left and the right channel, of course. Well, there you have it. I hope you enjoyed this analysis and repair of the Sencore PA-81. These things are in very high demand. They disappear almost immediately from eBay, whether they're working or not, probably because it's a nice, compact little device that can measure power, has the DC loads and everything. And perhaps in the future, we'll do some testing on some Class D high-power amplifiers using this device, as well as some other things that you just want to dump a lot of power into something. Let me know what you think. I'll see you next time.